This is measures of dispersion. How spread out is your data? Talked about when we were dealing with the mean that sometimes the mean doesn't really represent the data very well. Well, our first one we're going to look at is the range. This is the difference between largest value and the smallest value. Range is equal to largest value minus your smallest value. So, very simple formula. Let's take a look at an example of that. We have 33, 45, 5, 31, 50, and 85. Now range, remember, is our largest value minus our smallest value. Well, if my largest value is 85, which is in this example here, our smallest value is 5. So the range would be 80. Now this may not really represent the data that well. It just shows how spread out is it. It doesn't say how many are in the near the 20s, how many are near the 30s, or how many are near the 85s, for example. Just from the smallest to the largest. Now we got something called a standard deviation. This is a measure of variation of values about the mean. And we'll come back to these formulas in more detail, but we have a population standard deviation. This little O looking thing with the flip, that's lowercase sigma. And it says it's square root, and then remember this is uppercase sigma. That means we add together. So our x values minus the mean squared, and then add them together. Divided by capital M. Capital N is how many are in our total population. And mu is our population mean. Okay. Now our sample standard deviation. And that's S is equal to square root. And then I'm going to take the x values, subtract the sample mean, and square it, and then add them together, and then divide by n minus 1. Little n is how many is in my sample. We've got a shortcut formula, which we'll show that one, so we'll come back to that. Let's do this by hand. Okay, so we got 5, 10, 23, and 2. And standard deviation is something you should be able to do by hand, even though technology does it fantastic. I've had many students come back and tell me that other professors, other instructors in other classes will require them to show the steps by hand. Now I'm specifically going to find a sample standard deviation. The population standard deviation is the same formula, except for instead of dividing by n minus 1, you divide by n. So let's look at this one. First thing, our x values. The x sub I you see right here, the I represents you could have 1, 2, 3, 4, however many data points. So we're going to have 5, we'll have 10, we'll have 23, and we'll have 2. Okay. Now we need x bar, so I'm going to add these together, and just so I don't have any screw ups in my example here, I'm going to do this 5 plus 10 plus 23 plus 2. That gives us 40. Okay, I need to scroll down a little bit more space. Okay, so our x bar, we're going to take our 40, and we got 4 data values, so we'll divide by 4. So that gives us 10. That's our sample mean. Now from a formula here, it says x sub I minus x bar. So we need a column for x sub I minus x bar. So we're going to take this each of these x values, and we'll subtract the x bar. So 5 minus 10 will give us negative 5. And we got 10 minus 10, which gives us 0. 23 minus 10, which is 13, and 2 minus 10, which gives us negative 8. Now let me double check myself here. 5 minus 10, 10 minus 10, 23, 2, okay. 5, 0, 13, negative 8. That's what's inside of parentheses. Well, then we got squared, so we need another column. We're going to square those. So we're going to have negative 5 squared, which gives us 25. We're going to have 0 squared, which gives us 0. We'll have 13 squared, which is, I think, 169, but let me check. 169, yeah. And we're going to have negative 8 squared, which is 64. So that's this right here. X sub I minus x bar squared. Now we get this E looking thing in front of here. That's our uppercase sigma. That says now add those values together. So I want to add these values together. And I'm going to use technology here and not do it by hand. 25 plus 169 plus 64. And we get 258. Well, now we're ready to plug it into our formula. So S is equal to square root of the sum of xi minus x bar squared divided by n minus 1. Well, we just said the top part is 258. Now n is how many data points we have. Well, we have 4. So we have 4 minus 1. So we got 258 divided by 3. That actually goes into it evenly. What's that give us? 258 divided by 3. 86. And then square root of 86. If I plug that in my calculator, I get 9.3. Would be my sample mean. Now I put S there to represent sample mean. Now there's a shortcut formula to do that. Actually, let me mention population standard deviation first. Again, exactly the same formula, but instead of dividing by n minus 1, we just divide by n. So the difference on it is we divide by 4. I'm not going to actually create that, but you have to specifically look at what they're asking for. Are they asking for sample standard deviation or population standard deviation? There's a shortcut formula. So let's look at this in detail. Looks more complicated. I always show that to students. Well, that's more complicated. It looks more complicated, but it's missing an important piece. If I come up here, oops, right there, look at our sample standard deviation. This has got x bar. This doesn't have x bar. And you're saying, well, what's the big deal? It didn't look that bad. Well, I designed this to come out really nice. Imagine if you have a bunch of decimal places here. This was 10.137457913. Now you don't want to round it because you start rounding early on in your problem and you get errors. Well, when you put a bunch of decimals in here, this becomes nasty. The benefit of this formula is it doesn't revolve around the mean at all, so that there's less decimals. I shouldn't say there's none, because there is still some. Well, let's look at this problem reworked using the shortcut formula. So let me write down the problems down again. So we got 5, 10, 23, and 2. And we use our shortcut formula. Well, to begin with, I see over here we got sigma x, so I want to add together the x values. So let me first put the x values down, 5, 10, 23, and 2. And adding together the x values, and you can drop the sub I. What is that, 40? Now that would handle this piece right here. Now n's, I know that's how many we have. Now this is I need x squared. So I'm going to square each one of my x values. So I got 5 squared, I got 10 squared, and 23 squared, and 2 squared. 5 squared is 25, 100 squared is 100, have no clue about 23. Let's see, 23 squared is 529. And 2 squared is 4. Well, this sigma that's in front of it means I now want to add those together. So I'm going to sum these. And let me see, 25 plus 100 plus 529 plus 4. And we get 658. So now I have this, have this. I'm ready to plug in my formula, actually. So we got n sigma of x squared minus sigma x, all that squared, divided by n times n minus 1. Okay, now n would be 4, that's how many we have, times sigma x squared, that'd be 658, minus sigma x, 40, all that squared, over 4 times 4 minus 1. Okay, so let's see. 4 times 658 minus 40 squared, 1032. And 4 times 3 down below gives us 12. And square root of 1032 divided by 12. Get 9.3. And that's our sample standard deviation, which matches what we have here. But again, we didn't have the possibility of the X bar giving us some nasty decimals. Well, let's use technology to do this now. So let's go to our calculator and clear that out, exit out of here. I'll do second mode, exit out. Now I'm going to go into my stat, go into my edit. Now I want to put my numbers in. So I'll press delete over and over to clear those out. Quite a few numbers. Okay, so then we'll put in 5 inner, 10 inner, 23 inner, and 2 inner. Now this are steps from the last section, one of our stats. So do second mode to exit out. I'll go into my stat, right arrow to calc. One of our stats is selected, so we'll press enter on it. Now this assumes L1, and that's where we put our data, so we're fine. So we'll press enter again. Now the SX you see right here is your sample standard deviation, so that's your 9.3, which will give us the same value as if we'd done it by hand. Now on this test, I will ask you to do this by hand. And again, for the reason why some instructors expect you to know how to do it by hand. Now there's another problem that I may ask you to find a standard deviation on, and population or sample, and I won't specify by hand. Realize only if I say do it by hand, you need to pay attention to that. Because the other one may have 30 problems, may not come out, or 30 numbers, may not come out nice at all. Okay, so the SX is our sample standard deviation. The run right below it, that's O with a flip. That's our sigma X. That's our population standard deviation. So whether you're given a problem that's asking for sample standard deviation or population standard deviation, one of our stats will give you both of those. And okay, and I put the steps here to refresh your memory. Now if you just want to find a sample standard deviation, here's the buttons on how to do it. I don't like this. One of our stats does everything. Every semester I keep thinking I need to delete this slide. But if you are just curious and find the sample standard deviation alone, this is the buttons for doing it. Enter values into L1. Be sure to exit out, so do a second mode. Then we press second stat, choose math, choose standard deviation, enter second one to put L1 on there, closing parentheses, and then enter. Now our variance. The measure of variation equal to the square of the standard deviation. So I'd ask you for variance in a problem. Well, very simple. You'd square your standard deviation. So like here, when I get this value, I'd want to square it. So let me show you. Okay, so I've just done the square root of 1032 divided by 12. You can put a closing parentheses at the very end if you want. Don't have to have it. And we get this. We immediately press the x squared and press enter, and that would tell us our variance is 86. Now variance, in terms of the sample, as soon as I get my little pen to work here, there it goes, is represented by s squared. So that would be our sample variance. Now population variance is sigma squared, like that. So it's very simple. Now if I'm using technology, okay, so I'll go through and I do my one var. I've entered my numbers in. I go and do one var stats. So I press stat, right arrow to calc, do enter on one var stats, enter again. And I'm asked to find sample variance. Well, let me get a piece of paper. If you're not very good with technology, yet you're still trying to use it, you'd want to jot down the if you got the newer versions of the TI-84, you have to jot down the number, I think. So I'm going to do S is 9.273618495. Okay. Now, so what we're going to do is we're going to type that in, then we're going to press our x squared. So do 9. Now you notice how on mine it cleared the display. That's why I say I think, because the newer TI-84s is what this software is revolving around. And that's why you have to kind of jot it down before you start this. And then push your x squared button. And then enter. And that would give us our sample variance. Okay, let's say you're into technology. You've done your stat, you've done your calc, one var stats, and you come up with SX. There's a vars button here. If you press this vars button, the fifth one down are statistics. I'm going to down arrow to it and press enter on it. You can also press the number 5 directly and it does a down arrow and enter for you. Now once I go into that, you see the third one is our SX. So if I choose 3, then I don't want to have to type the number in. It'll handle that for me. And then I push the x squared and it'll give us that. Now notice there's no kind of rounding error on this either when you do it with this. Now these vars only work after you've done one var stats. They don't work if you've done just the single mathematical function, standard deviation, or mean. Those ones I said I should delete out. So if you've done one var stats, you can do that directly. Okay. Let's say it's asking for population standard deviation, population variance. Okay, I'll go through my steps on technology. I do my stat, I do my calc, I do my one var stats, press enter. Again, the sigma x here is your population standard deviation. So if I'm good in technology, if you're not good in technology, then jot that number down and then type it in and press your x squared. But if I'm good with technology, again, I'll push the vars, I'll choose statistics, press 5, I'll choose 4 for the sigma x, our population standard deviation, and then I'll push the x squared, and then enter. And that'll give us our population variance, if you had a problem asking for that. Now to review our symbols. These are the 6 very important ones. Throughout this class, you'll need to know what these represent, because you'll see them, and they won't always tell what they are. Let me grab a drink real quick. Our first one is S. This is sample standard deviation. S squared is sample variance. X bar, sample mean. Sigma is population standard deviation. Sigma squared is population variance. and mu is population mean. Now, in comparing two sets of data, the larger the standard deviation, the more dispersion the distribution has. So the one with the largest standard deviation is more spread out. Now, I left this this particular PowerPoint in. Doesn't really apply to the current textbook, but I felt there should be some kind of general rule. Round-off rule. Carry one more decimal place than is present in the original set of data. So over here, these didn't have any decimal places. So for my answer, I took it to one decimal place. I wish all books had some kind of convention for that. Some of them just kind of, sometimes it's 2, sometimes it's 4. And I know, depending upon the industry, depending upon what kind of precision they want, it would vary. But it'd be nice in books to be given that. Now, we don't do a whole lot with this in this class, so just besides just finding it. But this formula, the coefficient of variation, CV, this allows us to compare variation in different populations. And this describes the standard deviation relative to the mean as given by the following formula. CV equals standard deviation divided by mean times 100%. And I put those real generic because you could have a population values, population standard deviation, and population mean, or you could have sample. You could have sample standard deviation, sample mean. Let's take a look at example on that. And actually, let me save that page, and I got room for one more. Okay, so standard deviation, and let me say it's population values. So population standard deviation is sigma. So sigma is 2, and mu is our population mean, which would be 10. And it says find the coefficient of variation. Okay, let's go back to our formula. Formula says standard deviation divided by mean times 100. So standard deviation divided by mean times 100. And this is going to give it to us in percent form. That's 0.2 times 100, which should give us 20%. I hate decimals. Let's see, 0.2 times 100. Let me verify that. Yeah, 20%. Also, I hate making an hour movie and having a mathematical error in it, so I want to make sure. Now, again, this book doesn't do a whole lot of analysis of what does this represent and so forth. Just basically finds it. Now, another formula we can use to describe the skewness. Remember, skewness is when your data is skewed left or right. When you look at your bar graph, oops, I guess it's time to save it now. So, yes, measures of dispersion. A01. There we go. Remember, if we look at our data, and here's our bar graph, all the data appears to be on the left side. This is skewed right. So to describe the skewness of a distribution, this generally lies between -3 and 3. The closer it is to -3, the more it is skewed left. The closer it is to +3, the more it is skewed right. 0 indicates symmetric. Symmetric is where you get more or less your bell shape when you connect these together, the midpoints of your bar graph. Okay, so let's look at a formula dealing with this. It says mean is 60. The median is equal to 40. And our standard deviation is equal to 10. Well, how can you get this fairly fast? Well, one var stats gives you all this information, remember? Gives you mean, gives you median, and standard deviation. So if you've given raw data and they ask you to find the same thing, Well, use one of our stats, get these, and then plug them into your formula. Okay, so our skewness is equal to 3 times your mean minus the median divided by standard deviation. Okay, so mean was 60 minus the median, which was 40, over standard deviation, which is 10. 60 minus 40 is 20, times 3 gives us 60, so we've got 60 over 10, or 6. Closer it is to negative 3, more it's skewed left. The closer it is to positive 3, more it's skewed right. Well, this is a positive 6. It's way beyond plus 3, isn't it? So this is skewed right. And again, describe the skewness of the following. So, well, there's a very crude way to tell how spread out the data is. You can approximate the standard deviation by taking your high value minus your low value. That gives you your range, and then divide by 4. Well, it isn't a very good measure, but sometimes maybe that's all you have. Maybe you don't have your actual data. You're just given the high value and low value, and they ask you to approximate the standard deviation. So that'd be the formula you'd use. Now, this is a minimum usual values, mean minus 2 standard deviations, and the maximum usual values, mean plus 2 standard deviations. So, for example, I don't got a problem on this, but let me make one up. You know, if they give you the mean and the standard deviation, so let's give x bar is 10 and s is 2. Sample mean, sample standard deviation. And they ask you what are the usual values. Well, the usual values go from mean minus 2 standard deviations to mean plus 2 standard deviations. And we'll look at this formula a little bit more, but apply to any values. So if I put that in, I got 10 minus 2 times 2, and 10 plus 2 times 2. 2 times 2 is 4, so 10 minus 4 is 6. 2 times 2 is 4, 10 plus 4 is 14. So our usual values fall between 6 and 14. So if you had a data point that was like 17, that would be considered unusual, not normal. Most of them fall in this area. Excuse me. Now, some of the times in statistics, they just ask you, is this unusual? Well, what they're referring to is this formula right here, if they give you numbers. Now we got our empirical or bell-shaped distribution. Now this is a 68, 95, 99.7% rule. This says about 68% of all values fall within 1 standard deviation of the mean. About 95% of all values fall within 2 standard deviations. And about 99.7% of all values fall within 3 standard deviations. If I look at this, I see in my bell curve here, the middle 2, that's 68%. And they're symmetric, the bell shape is. So the left side here would be 34%, the right side would be 34%. Then 95% fall within 2 standard deviations. Now unfortunately the book has a little bit of a typo here. They put M for the mean. They should have put mu, because see how they put sigma for the standard deviation, which means they're talking about population values. Well, I stole this out of our particular textbook, so probably would have come up with my own if I had noticed that to very begin with. They probably meant to replace the M's with mu, but they didn't. Now you can have population values here, you can have sample values, doesn't matter. But anyway, here's M here are means exactly in the middle. Now here over here is mean plus sigma, that's mean plus 1 standard deviation. I go one more out, that's mean plus 2 standard deviations. And then mean plus 3, and so forth. And this shows all the percentage breakdowns that fall in each little bar over here. That's going to become important later on. Okay, the important part in statistics or in life is the 95%. That's what we go off of. I always tell students they never study to get 100% on a test. Nobody does. To study to get 100% on a test, you would have had to read the chapter 3 times maybe. Start studying for the test a week, 2 weeks in advance. Go see tutors, work every problem, not just what's assigned, but every problem you could ever run across. Maybe buy another stats book, so forth. Now this is to study to get 100% on a test, to ensure 100%. Maybe the night before you'd study 8 to 10 hours. We don't have that kind of time. That's ridiculous to spend that kind of time. Most people study maybe to get 95% on a test. 95% is pretty good. That's still an A, isn't it? And it's very reasonable in terms of time and expense and so forth. Maybe 95% means do the homework, study an hour the night before the test, and maybe get 95%. This is kind of true in life. We don't shoot for 100% because it costs too much. So we shoot for an A range, 95%. And 95% is kind of a magic number. Excuse me. Now, using the empirical rule to determine percentage. First thing you need is your mean and standard deviation, and you may have to use one var stats to get that if you're given raw data. Then you map the mean and standard deviations to a blank bell graph, and then you add up the appropriate percentages you are wanting to find in the problem. Well, let's look at a problem dealing with that. Okay, let me move some of this. I've got some junk in my way here. There we go. And this is problem 5. And let me make that a little bit bigger. There we go. Okay, given the mean equal 20 and standard deviation is 2, use the empirical rule to find the following. Use the empirical rule. So mean is 20, and let me, it doesn't specify what, sample or population, but let me say, just so I don't have to write a lot, we'll say it's sample. So mean is 20, S is equal to 2. It says use empirical rule, so let's go back to here. Exactly in the middle is our mean. So that'd be 20. Going one standard deviation on both sides, this would be x bar plus one standard deviation, that's S, not 5. That would be 20 plus, and then the sample standard deviation was 2, so that'd be 22. Now going out this way, this would be x bar minus S, so this would be 20 minus 2, or 18. Well, go another one out. This is x bar plus 2s. So we've got 20 plus 2 times 2, which gives us 24. And this one would be x bar, this is what we're talking about mapping them, minus 2s. This would be 20 minus 2 times 2, or 16. Now once you see a pattern on these are very easy. See how it goes from 20 to 22 to 24. So this next one, which is our x bar plus 3s, I don't even have to plug numbers in, I know it's going to be 26. And this one out here, that's x bar minus 3s, 18, 20, 16, 14. Okay, now this one here has 34% in it. This one has 34% in it, just looking at these. Next one is 13.5%. This will be 13.5%. It's symmetric. 2.35, 2.35, and 0.15. Okay, so let's go back to our problem. A. Determine the percentage that falls between 18 and 24, inclusive. Between 18 and 24. And I'm going to use red for this. Here's 18 and 24. So 18 and 24 would be from here to here. So I'm going to add up all the percentages in there. So I got 34% plus 34% plus 13.5%. And so I don't make a math error, let me plug this in. Let's see, 34 plus 34 plus 13.5. That gives me 81.5%. So it says determine the percentage that falls between that. Well, 81.5% falls between those. Now B, determine the percentage that is greater than or equal to 22. I'll make this blue. Greater than or equal to 22. Well, here's 22. Greater than or equal to. That'd be everything to the right. So these three here. So I'm going to add together the 13.5% plus 2.35% plus the 0.15%. Do that here. 3.5 plus 0.15. Of course, there's still a margin of error assumed with this that I'll type it in wrong into the calculator. That gives us 16%. Then C, I'll make it green, I guess. Determine a percentage that is less than or equal to 16 or greater than or equal to 24. So less than or equal to 16, here's 16. Less than or equal to would be that right there. Or greater than or equal to 24. Here's 24, so that'll be everything to the right. Okay, so here we got 0.15% plus 2.35%, and on this right side we'll have 2.35% and 0.15%. Oops. Now these add up to 4.7, and that's 0.3, so that gives us 5%. And that's how you work an empirical rule problem. Now again, sometimes they don't give you the X bar and S. You have to do one var stats first to get those. So let me save this. And we'll continue on. I didn't want to play Tetris battle right now. Go away. Okay. Let's go back to her. Now this is a note on if it asks you to find the actual percentage in a range with raw data. For example, let me work one over here. Given 3, 7, 15, 23, 35, 36, 37, 52, 81, and 103. Now the empirical rule isn't based upon the actual data. It's based upon an anticipation. Since it follows a bell-shaped curve, then we can predict this many fall in this range. But if the problem was actually asking you to find the actual percentage, find the actual percentage between 20 and 40. That's what this these steps are indicating right here. First thing, count how many are in the range. Let's say this is X. Between 20 and 40 would be this one, this one, this one, and this one. So there's 4 of them. So X would be 4. Second step, count how many there are total. Let's say this is in. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 of them total. Okay. Step 3, actual percentage is X divided by N times 100. So we got our X divided by N times 100. So we got 4 divided by 10 times 100. I think it's 40%, but let me double check. 4 divided by 10 times 100. 40%. So that's the actual percentage of them that falls between 20 and 40. Now we got Chebyshevs Theorem. The empirical rule if it's bell-shaped. And Chebyshevs Theorem says the proportion of any set of data lying within k standard deviations of the mean is always at least this. Now the neat part about Chebyshevs Theorem is it does not have to be a bell-shaped distribution. You'll find that this will hold true whether talking about skewed left, skewed right, or even the bell-shaped. Let me do an example of this. Say we want to find it within 2 standard deviations. Well, Chebyshevs theorem, we got 1 minus 1 over k squared. We've got 1 minus 1 over 2 squared, 1 minus 1/4, which gives us 3/4, or 0.75, which is 75%. So that says the proportion of any set of data lying within k standard deviations, the mean is always the least. So within 2 standard deviations, the proportion is always at least 75%. And I give those or that example plus another one here. If you plug in the 2, you get 75%. If you plug in the 3, you get 89%. Now, if you ever have a problem that asks you to find a range of values given the mean and standard deviation within so many standard deviations. So, for example, they give us x bar is 10, and sample standard deviation is 2, and they want to go within 2 standard deviations. Well, this is our k, so they're telling us k is 2. So our formula is x bar minus k times s comma x bar plus k times s. Now you may have to use one bar of stats to get x bar and s, but x bar is 10 minus k, which is 2, times our standard deviation, sample standard deviation, which was 2, and x bar plus 2, oops, not x bar, better go back to bed, 10 plus 2 times 2, 2 times 2 is 4, 10 minus 4 is 6, and then 2 times 2 here is 4, which gives us 14. So within 2 standard deviations, this is our range of values. I did this problem, I think, earlier. I don't seem to be very random with my numbers I make up. But anyway, there's the official formula where k can be any value. I think the one I did earlier, I hard-coded 2. And that's the end of that section, so let me save this. There we go. Stop the recorders. Gotta find the recorder. And then stop the other recorder. Okay, this is measures of central tendency and dispersion from group data. Now, what are we talking about there? Well, if you got a distribution here, let's see, this is 10, 20, 30, and this would be 19, 29, and 39. And we got our frequency, 20, 13, and 5. Okay. Now, if we want to find our average or our standard deviation, our mean standard deviation, if I look at this, the question will become, well, how many 10-year-olds are there? How many 19-year-olds? We don't know. We know there's 20 between 10 and 19, but we couldn't tell you how many 10-year-olds and how many 19-year-olds. So this is going to show you a method for finding the mean and standard deviation based upon group data. Now, it's not going to be what the real answer was, unless you're just real lucky. because we have no clue what the original set of data was. If we had 20 10-year-olds, again, it's going to be different than if we have 20 19-year-olds, if we're figuring the average. Well, our first one here is mean from frequency table. We got x bar is equal to, and then we got our sigma notation, that's adding together, f times x, where f is frequency and x is class midpoint. And then down below we divide by the sum of the frequencies. Now here's how we do it with technology. We'll come back to that. Let's first do it by hand, then let's do it via technology. Okay, so our first problem. We got ages 0 to 4, 5 to 9, 10 to 14, 15 to 19, and 20 to 24. Then we got our frequency, which is 3, 8, 5, 12, and 2. And the instructions are to find the mean. Now I don't say sample mean or population mean because it's the same formula. So let's come up here. And frequency is our f. So this right here is our f. We need a class midpoint. So let's find our midpoints. And this will be our x. Well, midpoint, remember we take our lower class limit of this class plus the next one. So we got 0 plus 5, and then we divide by 2. Well, that gives us 2.5. Now we can use our class width very easily to come up with the other ones. See how this goes from 0 to 5 to 10. It's adding 5 over and over. So 2.5 plus 5 gives us 7.5. Plus another 5 gives us 12.5. Gives us 17.5, gives us 22.5. So those would be our midpoints. Now this says f times x, which implies I'm going to need to have a column where I multiply f times x. So I got 3 times 2.5, I got 8 times 7.5, I got 5 times 12.5, I got 12 times 17.5, and I got 2 times 22.5. Okay, I'm going to use my calculator pretty heavy here because I don't want a math error in these videos. So 3 times 2.5, 7.5. 8 times 7.5 gives us 60. 5 times 12.5, 62.5. 12 times 17.5, 210. And 2 times 22.5 gives us 45. Okay. Now we got f times x, and then we got the sigma in front of it, uppercase sigma. That means we're going to add those together now. So we want to sum this column, and that'll be our f times x. So 7.5 plus 60 plus 62.5 plus 210 plus 45, and that gives us 385. Now the other thing we need for this is sum of the f's. So we want to sum together the frequencies. 3 plus 8 plus 5 plus 12 plus 2. That gives us 30. And now we have everything we need for our formula. So let's plug it in our formula. So x bar is equal to the sum of f times x over the sum of f. So that'd be 385 over 30. 5 divided by 30. we get, I'll take it to one decimal place, 12.8. And that'd be our mean. Sample mean, population mean, same difference. Okay, so that's how we did this one by hand. Well, let's use technology now. And we'll actually use part of this for our technology. Okay, mean from a frequency table. It says put midpoints in L1, frequency in L2. Well, you have to find your midpoints first. So here they are. So let's go to our calculator. Excuse me. Press Stat, go into Edit. If you got numbers in L1, go ahead and press Delete till they're all gone. If you have numbers in L2, you can right arrow over and press Delete on them till they're all gone. Okay, so L1. No memory. L1 midpoints. Okay, so let's put our midpoints there. So we got 2.5, 7.5, 12.5, 17.5, and 22.5. Now I'm going to right arrow over to L2, and it says to put frequency in L2. So our frequency, we got 385, so 385. We got 12 and 2, and 2. Okay, now I didn't put it here, but anytime you're inputting your numbers, you should exit out. So we'll exit out. Let's do second mode. Then it says do stat button, choose calc, choose one of our stats, and well, you can read those. So I'll press stat. Did I push it? Okay, my calc is just going real slow. Okay, press my stat button, press right arrow to calc. We want to choose one of our stats, so press enter on it. And we want to put in L1, comma L2. So I'll do second 1 to get L1. Comma's right here above the 7. The button above the 7 button. So comma, and then I'll do second 2 for L2. And then push enter. And we see our mean is 12.8, which is what we got by hand. So that's how you find the mean of a distribution table by hand and using the TA3, TA4 calculator. Okay, well, the next thing. Sample standard deviation from frequency table. And there's my example down there. Well, let's first talk about this. We got s is equal to square root, and then we got x sub I minus x bar squared times f, and then sum it. And then sum of f's minus 1. We're going to look at that formula a lot closer. And then we've got our population standard deviation, which is our x values minus our mean, population mean, then squared, then times the frequencies, and then divided by the sum of the frequencies. Now the formulas are very similar. The only difference is, and this is true kind of throughout, is see how we minus 1 here on the bottom, and here we don't do the minus 1. Now here's the instructions for doing it with technology. I'm going to skip over that. And then variance. Square the standard deviation you found. Be sure not to round the standard deviation any before you square it. Okay, like I say, we skipped over some of that. We're going to go back to it. I first want to show it by hand. And this is not necessarily a simple process by hand. Do I have enough room? Probably do. Okay, I'll try to do it here. So we've got our ages. 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49, 2, 4, 10, 2, 4, 10, 3, and 1. And that's our frequency. Okay, now find a sample standard deviation and sample variance. Let's go back up to our formula. Like I say, we'll look at it in detail now. Well, the We need our x values, which is the midpoints. Remember our midpoints, we take the lower class limit of the current class plus the lower class limit of the next one, divide by 2. So we got 0 plus 10 divided by 2, which gives us 5. Next one would be 10 plus 20 divided by 2, which gives us 10. Or you could just simply use your class width. See how this goes from 0 to 10 to 20? I'm adding 10 over and over. Ooh. Okay, obviously I can't do basic math this morning. Or this afternoon, whatever time it is. 10 plus 20 is 30. 30 divided by 2 is, oh yeah, 15. What am I doing? Okay, add 10 over and over. 25, 35, and 45. So those are our midpoints. Those also happen to correspond to our x's from our notation. That's our x. Now we need x bar, which is sample mean. So we have to go back, do this formula first to get the sample mean. Okay. So this formula says we're going to take f times x, frequency times class midpoint. So I need an f times x column. Well, this is our f's here. So we're going to take 2 times 5, which gives us 10. We'll take 4 times 15, which gives us 60. We'll take 10 times 25, which is 250. We'll take 3 times 35, 105. And we'll take 1 times 45. And that gives us 45. Okay. This then says we need to, the sigma in front of it says we need to add those together. So that's going to be f times x. So I got 10 plus 60 plus 250 plus 105 plus 45. So that gives us 470. And from our formula, we also need to add together the f's. That's for the denominator, what's downstairs. So add those together. 2 plus 4 plus 10 plus 3 plus 1. That gives us 20. Okay, so then our x bar from our formula, this one right here, we're going to take the sum of f times x divided by the sum of f. So that gives us 470 divided by 20, which gives us 23.5. Okay. Let's go back to our formula. Okay, so now we got our midpoints, got the x bar, so we need to have a column for x minus x bar. So I'm going to take each x value. This would be 5 minus x bar, which is 23.5. And I got 15 minus 23.5. I got 25, 35, and 45. Minus 23.5 minus 23.5 minus 23.5. This gives us negative 18.5. This next one gives us negative 8.5. Next one is 1.5. Next one's 11.5. And next one's 21.5. That's what's inside the parentheses here. Well, now we want it squared. So I'm going to have a column. Some people put this all in one column, and that's kind of up to you, but where I'm going to square these. I like to build a piece at a time. So I got negative 18.5 squared. I got negative 8.5 squared. I got 1.5 squared. I got 11.5 squared. And I got 21.5 squared. 18.5 squared is 342.25. 8.5 squared, 72.25. 1.5 squared gives us 2.25. 11.5 squared gives us 132.25. And 21.5 squared gives us 462.25. Okay, last. We got it squared now, so now we're going to multiply times f. This is x minus x bar squared times f. So we'll take 342.25 times f, which was 2. And we'll take 72.25 times f, which is 4. We'll take 2.25 times f, which is 10. We'll take 132.25 times f, which is 3. And 462.25 times f, which is 1. That's 462.25. 342.25 times 2. 684.5. 72.25 times 4. 289. 2.25 times 10 gives us 22.5. And 132.25 times 3 gives us 396, excuse me, 0.75. Okay, so we've done all of this. So now the sigma out in front says now add it together. So I got 684.5 plus 289 plus 22.5 plus 396.75 plus 462.25. Oh, that's weird. 1855 comes out nice. Assuming I typed everything in correctly, which is always questionable. These are so easy to make a mistake on. Now the other thing we need is add the f's together. Well, we already have that over here. We added the f since 20. So now we're ready to plug in our formula. So our sample standard deviation is equal to square root of top part, x minus x bar squared times f over square root of f minus 1. Okay, so that gives us square root of 1855 over 20 minus 1. Probably better to do a little bit of simplifying before you plug it in your calculator. 20 minus 1 is 19. And now I'll go to my calculator. So I got the square root of 1855 divided by 19. We've got 9.880869342. Okay, so that's approximately 9.9 for S. Let me do one more thing before I show you use technology. I'm not going to do the population standard deviation. Basically the same formula, except we don't do a -1 down here. Variance. Square the standard deviation you found. Be sure not to round the standard deviation any before you square it. And I put all these decimal places here because when I'm finding the sample variance, I'm going to take all these and press my x squared and press enter. And then we get 97, and I'm going to round this because I'm not going to need it anymore. So 97.6. So this is our sample standard deviation, that's our sample variance. Okay, let's use technology now. We'll need part of this up here. I kind of skipped over this slide. This is how we're going to do it with technology. So let's take a look at this. It says put midpoints in L1. So let's start there. I go to Stat. I do enter on edit. I got data in L2 and L1. I'm going to press delete over and over until those are gone. Left arrow over. Again, do not press delete on L1 and L2. If you delete it by accident, I've given you steps up above on how to add it back in. Okay, so midpoints in L1. Try it again. Okay, here's where's our midpoints. 5, 15, 25, 35, 45. So we got 5, 15, 25, 35, 45. That's our midpoints. Okay. Frequency in L2. So our frequency was right here, 2, 4, 10, 3, 1. So I'm going to right arrow over. 2, 4, 10. I'm pressing enter after each one. 3 and 1. Okay, now it doesn't say it, but after we input those in, we have to exit out. So be sure to do a second mode to exit out. And we're just going to do one var stats L1, L2. So I press my stat button, right arrow to calc, enter on one var stats, then second one, comma, second 2. A lot of people forget the comma. I have to have the comma there. And then push enter. And assuming I did my math correctly, this should match up against our by hand answer. Our by hand answer is 9.9. This is 9.9. So that looks good. I won't have to curse and redo the video. Again, technology is much easier to do that. Now, usually on tests, I don't have people create this by hand. But you do have the example there in case you ever need to refer back to it of how to do it. Okay, let's talk about a weighted mean. Here we have x bar of our weighted mean. That's what that W represents. Now here we have sigma W times x, and then down below is sigma W. W is the weight of the ith observation, and the xi is the value of the ith observation. So let's do an example. And actually I'll need a new page because I filled it up with these. And what in the world is this? Measures central tendency and dispersion from group data. What a mouthful. Okay, measures. Actually, I got it right here, don't I? Measures the central tendency and dispersion from group data. Okay. Then down here, page 01. And then click save. Okay. So let's look at this example. It says, in a course, attendance counts for 10% of the grade, quizzes count for 20%, weight tests count for 50%, and finals 20%. Bill got 100% for attendance, 80% for quizzes, 70% for tests, and 30% on the final. He should have studied harder. What is Bill's course average? Well, let me reposition myself in my seat here. There we go. Okay. Now we need we need our W's, the weights, and we need our X values, the the actual observations. So we need our W's and we need our X's. Now W's are weights. Let's go back and read the problem. We've got our attendance. And it says attendance accounts for 10% of the grade. So my weight there is 10%. And I'll put that in decimal form. Next one is quizzes. Count for 20%. So that's my weight. It's worth 20%. Tests count for 50. So this would be 0.50. And final as 20%. So that'd be 20%. Okay, now what were the actual values they got? Bill got 100% for attendance. So he got 100%. 80% for quizzes, so he got 80% there. 70% for tests, that was his average. And 30% on final, so he got 30. And then it says, what is Bill's course average? We'll use weighted mean for that. Okay, now this means W times X. It means I need a column W times X. Nothing exciting there. We're going to take 0.10 times 100. We'll take 0.20 times 80. 0.50 times 70. And 0.20 times 30. I'm not very good with decimals. So I'm going to use my calculator. I don't want to make a math there after I've done so well on the harder problems before this. So 0.10 times 100 is 10. I think the next one's 16, but let's see. 0.20 times 80. Yeah, 16. I think next one's 35, but let's see. 0.50 times 70. Yep, 35. Next one, 0.20 times 30. And we get 6. Okay, so that's W times X. We got sigma in front of it, which means add them together. 26, 32, 62, 67. Let me double check. 10 plus 16 plus 35 plus 6, 67. And then down below here, we got add together the weights. So over here with our weights, we're going to add these together. 7, 9, 10. So this adds up to 1. Then our weighted mean is going to equal to the sigma W times X over sigma W. So we got 67 over 1 or 67. So his grade for the course would be 67. And I think that's the last slide. Yes, it is. So let me save this. There we go. And stop the different recorders. I guess I got to find this recorder first. Sometimes WebEx hides theirs. There we go. Stop the. And stop the other recorder.